Episode 52, titled Sparse Data and High Dimensionality, Symptoms and Mitigations. The goal is to recognize sparse data traps early, because these traps produce unstable models that look impressive in development and then collapse when exposed to new data.
Sparse, high-dimensional datasets are common in modern analytics, especially when you convert categories into many indicator features, track event counts across many possible actions, or represent text and logs as large vocabularies. The exam cares because these conditions change what modeling assumptions are safe, what evaluation is trustworthy, and what mitigations are appropriate.
In practice, the main danger is not that the data is too big, but that it is too empty, too wide, and too easy to overfit with patterns that do not generalize.
When you can diagnose these conditions from symptoms, you can choose simplifications that preserve signal without pretending that more features automatically means more knowledge.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.me in the Bare Metal Study Guide series.
Sparsity means that across many features, most entries are zero or missing, so the dataset contains far more absence than presence.
This is common when features represent rare events, such as specific error codes, uncommon user actions, or unusual alert types, where the vast majority of records do not contain that event.
Sparsity can also appear when data is assembled from multiple sources with uneven coverage, so many fields are missing for many records, because not all systems populate them. A sparse matrix can still be informative if the non-zero entries carry strong signal, but it can also be brittle because small changes in which rare events appear can shift learned patterns.
The exam often signals sparsity with phrases like mostly zeros, many missing values, or high cardinality one-hot encoding, and the correct response is to treat that structure as a modeling constraint. When you narrate sparsity, you are describing a dataset where information is concentrated in few places and absence dominates the representation.
High dimensionality describes the situation where you have many columns relative to the number of rows, meaning the feature space is large compared to the amount of evidence you have to learn stable relationships. This can happen because the dataset truly has many distinct variables, or because feature engineering has expanded a smaller set of concepts into many derived indicators. The practical problem is that when dimensions grow, it becomes easier for a flexible model to find patterns that fit the training data by chance because there are many degrees of freedom to exploit. High dimensionality also makes estimates less stable because small changes in the dataset can change which features appear influential, especially when many features are correlated or redundant. The exam cares because more features sounds like more information. But in high-dimensional settings, it can mean more ways to fool yourself. When you notice high dimensionality, you should immediately think about controls against overfitting and strategies to reduce the effective complexity.
One effect that grows with dimensionality is that distance measures degrade as dimensions increase greatly, which is a core reason why some intuitive methods behave strangely in high-dimensional spaces. In low dimensions, distance can separate near and far points in a meaningful way, but as dimensions grow, points tend to become similarly distant from each other, making nearest neighbor logic less discriminating.
This is especially problematic when many dimensions are sparse or noisy, because the distance metric is influenced by many irrelevant differences and many shared zeros that do not necessarily indicate true similarity. The result is that clustering and similarity-based retrieval can become unstable or produce groupings that do not reflect real structure because the geometry becomes less informative. The exam may not require formal proofs, but it expects you to recognize that high dimension changes the behavior of distance-based approaches and can reduce their reliability. When you narrate this effect, you are essentially saying that geometry loses contrast, so methods that depend on contrast need careful handling or alternative representations.
Overfitting risk rises sharply when features outnumber useful signal, because the model can memorize quirks rather than learn durable patterns.
This is not only about the count of features, it is about the ratio of complexity to evidence, and in sparse settings, the evidence for many features is thin because each rare feature appears only a few times.
Overfitting shows up as strong training performance with weak validation performance, unstable feature importance, and large swings when you retrain on a slightly different sample.
It can also show up as a model that seems to learn rules that are really data artifacts, such as treating a rare code as decisive because it happened to correlate with the target in a small subset.
The exam will often describe a model that performs well in development but fails in production, and high-dimensional overfitting is a common cause, especially when feature generation is aggressive.
When you recognize that the feature space is rich but the signal is thin, you should default toward methods that constrain complexity rather than amplify it.
Regularization is one of the most direct mitigations because it reduces sensitivity to irrelevant features by penalizing complexity. The intuition is that the model should not be allowed to assign large influence to a feature unless the evidence supports it, and regularization enforces that by shrinking coefficients or limiting effective degrees of freedom. In linear models, regularization can reduce variance and improve generalization, especially when many features are correlated or when many features are weakly informative. In high-dimensional settings, regularization often turns a fragile model into a stable one because it resists chasing noise in rare indicators. The exam expects you to know that regularization is not a data cleaning step, but a modeling strategy that trades a bit of bias for a potentially large reduction in variance. When you narrate regularization, you are describing a deliberate preference for simpler explanations unless the data strongly argues otherwise. Dimensionality reduction is another mitigation when structure exists but features overwhelm the learning process because it seeks to represent the dataset in a smaller set of informative components. The key idea is that many high-dimensional datasets have hidden structure, such as correlated groups of features, latent topics, or underlying factors that drive multiple measurements. By compressing into fewer dimensions, you can reduce noise, improve stability, and make distance-based or linear methods behave more predictably. Dimensionality reduction is not always appropriate, especially if interpretability requires keeping original features, but it can be valuable when the goal is robust prediction or clustering rather than direct feature attribution. The exam often uses terms like principal component analysis or embeddings in this context, and the correct reasoning is that reduction can preserve major structure while discarding fragile variation. When you apply this mitigation, you are acknowledging that the raw feature space is too wide to learn from directly with limited evidence.
Feature selection is a complementary approach that drops redundant or low-value variables rather than transforming them, and it is often easier to justify when interpretability matters.
In sparse, high-dimensional data, many features carry little information because they are nearly constant, extremely rare, or dominated by missingness, and removing them can reduce noise and computation.
Redundancy is also common, where multiple features encode the same concept or are highly correlated, and selection can reduce multicollinearity and stabilize models that otherwise struggle to attribute effect. The exam tends to reward feature selection reasoning when it is tied to evidence, such as removing near-zero variance features or collapsing redundant indicators rather than arbitrary pruning. Selection also helps with operational maintainability, because fewer features means fewer data dependencies and fewer ways for pipelines to break. When you narrate feature selection well, you emphasize that simplification is not loss of rigor. It is a method of protecting generalization and stability.
High cardinality categorical features deserve special mention because they are a common source of both sparsity and high dimensionality, especially when encoded into many indicators.
A feature like user identifier, device model, or URL path can explode into thousands or millions of distinct values, and naive encoding can create a matrix that is mostly zeros with a tiny number of ones per row. Hashing can mitigate this by mapping many categories into a fixed-size representation, reducing dimensionality while accepting controlled collisions that trade exact identity for manageable representation. Embeddings can also represent categories in a lower dimensional continuous space, capturing similarity structure if it exists, and improving generalization to rare categories by sharing statistical strength.
The exam expects you to understand that these techniques are not magic, but practical compromises that manage the curse of high cardinality without discarding the signal entirely. When you choose these approaches, you are explicitly responding to representation constraints created by category explosion.
Model choice also matters, because some model families naturally handle sparsity better than others, and the exam often tests whether you can match model behavior to data structure. Linear models can work well in sparse settings, especially with appropriate regularization, because they scale and can generalize effectively when signal is distributed across many weak features. Tree-based models can also handle mixed feature types and nonlinearities, but they can struggle with extremely high cardinality sparse indicators by overfitting to rare splits unless constraints are applied. The correct choice depends on the data's sparsity pattern, the expected relationship structure, and the need for interpretability. But the key exam skill is to recognize that sparse, high-dimensional data requires models that constrain complexity and can learn from limited evidence per feature. You should also be alert to how you represent missingness, because some models treat missing values natively, while others require explicit handling that can add dimensions. When you narrate model selection here, you are emphasizing alignment between data structure and algorithmic assumptions rather than chasing a popular method.
A practical operational pitfall is dense conversion, where sparse representations are turned into dense matrices that explode memory and compute costs without adding information. In a sparse matrix, storing only the non-zero entries is efficient, but a dense conversion forces the system to allocate space for every zero, which can be catastrophic when dimensions are large. This is not just a performance concern. It can change how workflows are designed, whether you can train at all, and whether evaluation becomes slow enough that teams start cutting corners. The exam may include a scenario where a pipeline fails due to resource constraints, and the underlying issue can be inefficient representation rather than the algorithm itself.
Avoiding dense conversion is also part of methodological discipline because it keeps you honest about the true information content and encourages representations designed for sparsity. When you recognize this pitfall, you are thinking like someone who understands that computation is part of the system, not an afterthought.
Validation becomes more important, not less, in sparse, high-dimensional settings, because these are the environments where models can fool you most easily. You need strong splits that reflect how the model will be used, because random splits can accidentally share rare features or near-duplicate patterns across training and validation, inflating apparent performance. Temporal splits, group-based splits, or other leakage-resistant designs can help ensure that generalization remains real rather than an artifact of shared structure. You should also expect higher variance in performance estimates because sparse features can appear or disappear across samples, and that variability should be reflected in how cautiously you interpret results. The exam often tests whether you will trust a single high score without checking stability, and the correct posture is to demand evidence that performance is robust across splits and conditions. When you narrate validation here, you are emphasizing that sparse data requires stronger proof of generalization, because the temptation and capacity to overfit is higher.
A helpful anchor memory is too many features, too little signal. Simplify wisely.
Too many features is the condition that creates the space for false patterns. Too little signal is the reality that limits what you can learn. And simplify wisely is the discipline of choosing mitigations that reduce complexity without discarding the structure you need.
Simplification can mean regularization, dimensionality reduction, feature selection, hashing, embeddings, or constrained model choices, and the right mix depends on the dataset's shape and the decision context.
The anchor also protects you from the false belief that complexity is always progress, because in high-dimensional sparse settings, complexity often amplifies noise rather than insight.
On the exam, this anchor helps you eliminate answers that add more features or more complexity as a default response to instability, because the safer move is usually to constrain and compress.
When you use the anchor, you keep your reasoning aligned with the core risk. The model has too much freedom relative to the evidence.
To conclude episode 52, name one symptom and then choose one mitigation strategy, because this pairing demonstrates that you can diagnose and respond rather than recite definitions.
A common symptom is that validation performance is unstable across splits, with large swings in metrics and changing feature importance, suggesting the model is fitting fragile patterns in sparse indicators rather than durable structure. A suitable mitigation strategy is to apply stronger regularization in a linear model, because it reduces sensitivity to irrelevant or rare features and tends to improve generalization in high-dimensional sparse spaces. You would then validate with leakage-resistant splits to confirm that the improvement is real and stable, rather than a side effect of a particular random partition. This is the disciplined pattern the exam wants. Recognize the sparse high-dimensional condition, anticipate its failure modes, and choose a mitigation that simplifies the learning problem without ignoring the underlying signal.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.